Hey, John here. I was just thinking about some of the differences between the IMSAI 8080 and the Altair 8800. Now, we all know that the IMSAI 8080 is right here in paragraph 1 on Wikipedia, is considered to be a clone of the Altair 8800. And it obviously is, because if you look at it, the schematic level of the front panels in the S100 bus and the power and everything else, it is 100% influenced by the Altair. Now, how do we know which one came first? If you weren't alive back then, FYI, the Altair was available in January 1975, and it was orderable that Christmas of 1974 as well, by the way. So this was, if you had a very generous benefactor, you would maybe have gotten one of these things. Now, $439 doesn't sound like too much. But if you convert that to modern dollars, we're looking at $2,200 for this system here. Now, not quite as pictured either, by the way. That would have been the empty box with a CPU and a front panel, no memory, no hard drive, no disk, no floppy, no nothing, okay? And by the way, if you're soldering impaired, you would have ordered the $621 version, which in more modern dollars, and these are 2021 dollars too, by the way. All the inflation going on right now, I don't even want to think about what it would cost in 2022 dollars. Anyway, we're looking at more than $3,000 for this thing with no memory and no peripherals. Yikes. Okay, that's not a cheap thing. So the 8080 comes by basically a year later. And it, like I said, it's a very close knockoff, but there are some differences. I mentioned before that the power supply in the 8080 is far more robust than the one in the 8800, okay? This was well known to not quite have enough wattage to run all the boards and stuff like that. Also, this machine here, let me see if I can open this picture up here, which we can show because they're from Wikipedia with Creative Commons shared photos, yada, yada, yada. This is kind of a neat thing. It's got a plastic cover. Mine's missing its cover, or one of mine has a missing cover. It might be cool for me to go get some polycarbonate and maybe make one like this for mine that doesn't have a cover. That's a good idea. I should try that. Anyway, where was I going with this? The MITS Altair did not have the 22-slot motherboard like the 8080 does. What it had were a couple of small motherboards all stitched together inside, and the total wattage from the power supply would be depleted if you put several of the little motherboards in there and connected them all together and filled it up with a lot of memory. It would draw a lot of wattage, and you could end up with some problems. Okay. Anyway, the power aside, and I'm sure that you could just easily go buy replacement transformers or something like that, or even go with an external power supply if you had to, if you really wanted to load it up with a lot of memory cards. That's not the worst thing that could ever happen. It's a little annoying, given the price of these things. It would be nice if they had decent power. So anyway, the IMSAI decided that they wouldn't get caught with their power supply down, as it were, and put the massive transformer in there so that they wouldn't have that problem. Okay, so also, by the way, if memory serves, this was available at roughly the same price. You couldn't compete by selling a more expensive one, but it was around $450, if I recall correctly, for the kit version of this system. So what else then is different? All right. So if we look at close look at the Altair's front panel here, and you compare it to the front panel of the IMSAI 8080, what's different about these things, right? Well, the 8080 has one big long row of switches here, and the Altair has two rows of switches like this. It's not a big deal. So what? So you got a bunch of switches over here. And these are the toggle up and down ones, which have the similar functionality, the switches over here on the 8080. So let's count them out, make sure we got all the apples to apples here, right? So there's 8 switches here, 8 switches there. All these switches combined represent a 16-bit address value that show up on 18 or 16 LEDs along in here and grouped into 2 sets of 8, which are subgrouped into 2 sets of 4. Now, if you look really closely at this panel in here, it says hexadecimal there, octal there, and there's little bars, these slugs that print and group this into a set of 3 bits, a set of 3 bits, a set of 2 bits. And again, over here, we got 3, 3, and 2. So if you want to think in octal, they do give you little markers here to indicate where the bits the groupings of 3 would go. Or if you want to think in terms of hex, you've got 4 and 4 and 4 and 4. And I've never seen one colored different than the way this one is built right here. If you've got a picture of one, please send it. I actually put one of these front panels together, an original one from a kit, and I remember reading some note somewhere buried in the instructions that you're free to, obviously, put 3 reds, 3 blues, 2 reds, another red here, and then 3 blues, and so on, and group them for octal use or group them in 4, 4, 4, and 4 for hex use. But honestly, I've never seen one or a photo of one that has groupings of 3s on the IMSAI 8080. On the other hand, the Altair is grouped in 3s. And because these switches are mounted in drilled holes in a metal panel here, you would not have an option of grouping them into 4s if you wanted to. This thing is definitely designed to be used and thought of in terms of octal. So you've got 3 bits, and 2 bits. Now, I never really got into this whole octal thing. Never worked for me. It always felt unnatural because an 8-bit byte is not divisible by 3. You have these 3, 3, and 2, and it manifests itself in the fact that if you were to express values in octal, the octal digit that represents these 2 bits would be 0 through 3. The octal digit for this position here would be 0 through 7, and this would be 0 through 7. The fact that we don't have perfect symmetry there or consistency for each one of these, 777 would have made more sense. Well, that would have been a 9-bit byte instead of an 8-bit byte. So, and then you take that one step further. If you think of the 16-bit address LEDs, which are down here, and 3 and 3 and 3 and 3 and then 1, you still have this weird thing. And what's further, the least significant byte of the address, if you think about it in terms of the fact that it really is expressed as 2 bytes, and a lot of the instructions inside this 8080 processor and the Z80 as well, you've got this 3 and 3 and then 2 for the least significant byte over here. And then you've got 1 and 3 and 3 and 1 over there. This, to me, I'm like, oh, horrible. Yuck. I know. I'm too, I don't know, anal retentive. I don't know what it is. I want more consistency than we get with that. That would drive me nuts. But, as we'll see in a minute, there's a very good reason why you'd like to do this. There's actually kind of a neat reason why you'd want to do this. I mean, the people that built this are not stupid. Give me a break. Probably smarter than me, easily. Otherwise, I would have started a business like this back in the old days and gone bankrupt within 3 or 4 years, just like everyone else did. But nonetheless, the groupings we'll see in a minute do make sense. But again, I would just run my hair the wrong way. I don't like octal. I don't like the way these are grouped. So the biggest annoyance here, as you recall from the IMSAI 8080, the Altair 8800 also has this notion where the most significant byte of the address switches here, and you can see a little marking over there that says sense switch, sense SW. What that is a label on is it's telling you that these 8 switches here represent the programmed 8-bit input that you can access from a running program. If you ever input from port FF, you can read these 8 switches. Now, if you think about that, you got this 1, 3, 3, 1 thing going on, and you can see these little vertical marks. Let's see if we can zoom in. Oh, yeah, that's much better. I should have done that earlier. I'm sorry. You've got this 3 here, even though they're physically 1 and 2, and then you got another 1 and 2, and then yuck! This would drive me insane if I used it very often. Now, again, in their defense, you wouldn't use it all that often. Once you got your system up and running, you didn't really use the front panel that much. If you did at all, you would use the sense switches in here and read them during your boot ROM loader or something like that, and you could set these switches to as a command or something. So you could say, I want to run boot up from device A. Maybe you have a paper tape versus a floppy disk or a cassette drive, or maybe it would just go into a ROM monitor that's in ROM, and you could toggle in a different value on these 8 switches as your boot configuration parameters to tell that boot ROM what to do. And in that case, it really doesn't matter how they're grouped or anything, because you're probably not really even thinking about it. In either octal or hex, you're just probably going to just think that this top switch here up means boot into the boot ROM monitor, and when it's down, you boot into the floppy or something like that. So again, it's not really that big of a deal, other than the fact that it just doesn't feel natural to me to group these into 3s. All right, so what else have we got here that's different between the 8080 and the 8800? So they've got some LEDs over here and some up here. Well, the IMSAI 8080, so here's your 16 LEDs down here. I probably should have turned it on and lit them up so you can see the dots, but you can sort of see them in this photo anyway. The 8 data bit LEDs are here. So these 8 data bits and these 16 bits there perfectly match the 8 data bits here and the 16 data bits over there. Okay? Well, what about these up here? What do we got? From right to left, we got int, right out, stack, halt, A, out, M1, input, memory read. What do we got here? Int A, right out, stack, halt, A, out, M1, input, memory read. These match exactly these here, okay, on where it says status. So far, so good. Now we got 4 LEDs over here. You got prot, interrupt enable, wait, hold A. So we got your what? Here's your hold, which I think is the same as hold A. And what do we interrupt enabled? He's got interrupt enabled here. So then he has a wait and this prot. Well, here's your wait, and we don't have a prot, but we have a run. So given all the LEDs in this area of the 8080, the only difference is that we have an LED that goes on when the system's running on the 8080, and we don't have one on the 8800. There's no run light on here. It's just simply that if it's not waiting, it must be running, which is usually pretty obvious because all these lights are flickering like crazy. It's pretty obvious when these things are running. You don't need an LED telling you it's running. But this has this prot LED over here. Let's take a minute and put a pin in that for a second. What do we got off on? There's your power. You got stop, run, single step. You got examine next, deposit next, reset, clear. And we're back to this protect. And a couple of aux switches. These aux switches, as I understand it, were never hooked up to anything in the original kit. They're obviously there for you to play around with and customize how you want. I'm not familiar with what anybody commonly did with those. I'd love to hear about it. Throw some comments below if you got any tips and tricks up your sleeve there, right? So what do we got here? Okay, so power, stop, run, single step, examine, deposit, next, yada, yada, yada. So here's our power. Not in the same order. You got examine, next, deposit, reset, external clear, which is identical to what this thing here does. He just calls it clear. If you look at the schematic, this is the external clear. And it's documented as a system-specific function that can be used by your cards if they need to have some sort of a clear signal sent to them. So yeah, they're compatible. We got a run and a stop and single step. So he's got run, stop over here. His single step is a single-way toggle. You just push it down to single step. There's no push up, as far as I know. I don't believe there is. Well, this one you can push it down to single stick it, or you can push it up to click it single step it, either way. Okay, so what? So far, so good. The only difference so far then is this protect switch here and the protect switch LED up there that you have on the 8800 and you don't have on the IMSAI 8080. Now, put a pin in that for a second. What about this? Programmed output 0 through 7. As you might recall, I've talked about this before. This is an 8-bit value that, in my mind, it complements this programmed input value. Okay, so just like the Altair, if I want to, if I read from port FF, do an input operation on that, I can read the position of these 8 switches in my running program, just like I can this sense switch input on the Altair. They call it sense switch. The IMSAI 8080 calls it programmed input. It's the exact same thing, same port number, everything. So that's perfectly compatible. What about this? There's 8 bits of LEDs here. Anytime I output to port FF on an IMSAI 8080, I can put an 8-bit value on these 8 LEDs up here. There are no such LEDs on the Altair 8800. So this is missing 8 LEDs completely, and it causes a certain asymmetry. Now, you save up your pennies and you got a paper route that you do for 5 years, save up your money and you buy yourself a nice Altair 8800 and you want to play around with it. You can use these switches to toggle values into the address bus and the data bus. You can store a program in there and you can run that program. And that program can read these sense switches by inputting to port FF, and it can read their value. It can do different things and act in different ways, and you can control it. This could be your input device to running program. But unfortunately, this system here does not have any form of output. Well, the 8080 does. So you've got 8 input bits and 8 output bits. And I can assure you, to a 15-year-old kid, when I first got into all this stuff in the late 70s, that would have kept me busy for like 2 years. Just the fascination of learning how to make the thing go and get everything to work, it would have been more than enough fun. And these 8 LEDs would have been a godsend to supporting all that. Having them missing over here on the Altair is an unfortunate downside. However, we'll see in a minute that there is a way out of that. It's rather clever in a program called Killbits that you see floating around the net. This was obviously originally designed for the Altair. I highlight this date as my #1 form of proof because it was allegedly written in May of 1975. The 8080 was not available until December of 1975. So pretty sure this was designed originally for the Altair. Other clue, make it easier to enter into the Altair, and it gives you the octal values of all the bytes that you would need to enter into the machine using these switches over here, which are grouped for octal data entry. Okay. Now, I came along, honestly, probably around 1978, maybe 77, 78. I don't really remember when I first got into all this. I think it was 1978. And I never honestly heard of octal. I first heard of assembly language after being exposed to BASIC on a TRS-80. And I was just enamored with the whole idea. I had already done some electronics and done some digital electronics as well, ANDs and OR gates and stuff like that. So I kind of got the general gist, but not all the gist, and went to town playing with BASIC until somebody introduced me to assembly language, and the speed difference between BASIC and assembly the only way that I can explain the difference is to cite the scene from what is it, Ford versus Ferrari. If you've seen the movie, this is the first time Ford gets into this car, and this guy's trying to get him in the right mindset, and he's probably the first time. Ford Jr. over here has ever driven over 100 miles an hour. So the scene in the movie is really shocked this guy. Here's Ford over here, and that's Shelby. The character that plays Shelby is Matt Damon over here, and he just wants to show him what a car can really do when it's driven properly. So this guy freaks out completely. He's stunned. Let's just skip over until they get to the point where he can actually say a word. Boy. All right. I had no idea. To me, that's me in high school, the first time I wrote an assembly language program. It blew my mind off. I couldn't believe the speed difference. It was that moment in time where I no longer cared about BASIC or any of these interpreted languages. Holy mackerel, did it go much faster. So I really got into it at that time. Point being, the world started looking like this. Now, this is written in 8080 assembly pneumatics, but we know that the Z80 is a superset of the 8080, and I've been doing a lot of work with the Z80 lately, so if you've been following along that stuff on my channel, these are then going to look a little bit different, but nonetheless, they're the same thing. Now, even in this time, okay, when you ran this through an assembler, the assembler would express the opcodes and the operands all in hex. And that was my first experience as well. In fact, it was the EdTASM assembler on a TRS-80 was my first real exposure to this whole thing. Now, I just thought the whole world was in hex. So when I saw octal and I saw it used on machines with this kind of grouping, and I was like, oh, this is unnatural and very strange. Okay, now let's look a little bit about why the octal is in there and what we can do about this, these missing display bits on the Altair. Okay, so let's look at first this part of the manual. This now, what am I on page here? 23. This is the 8080, what is it, user guide or the assembly programming reference manual. Now, it turns out this instruction right here, this encoding format here, I'm on what page of this thing? So here's 16, I'm on page 17 of this manual. You see how this thing is encoded? Now this, I would argue, is mainly a coincidence. All right, it's not by happenstance, but when the engineers designed the 8080, they decided that they would have 7 registers in it. And when you have an instruction that refers to one of those registers, it has to represent which register it wants to use. If I'm going to add something or subtract or AND it, or it XOR, or compare something, okay? I have to identify which register I want to use. Now, these instructions, what they all do is they compare a value of a register, the contents of some register, with the accumulator. So the accumulator is an implied operand of every one of these instructions using these mnemonics, and again in the 8080, right? So if I wanted to add the value of register B to the accumulator, what I would need to do is I would have to tell the machine I want to do an add, and that is a 000. I put 3 zeros into these 3 bits right here. I set the most significant 2 bits to a 1 and a 0. These 2 bits over here tell the CPU that I need to do an ALU operation. This 3 bits here from this table here tell me what ALU operation I want to do. And because all of them use the accumulator for the target where the value will be stored, as well as one of the source operands. Okay, so if I said add B on the 8080, that's the same thing in the Z80. You might say add A comma B, that sort of a thing. Although the Z80 is somewhat inconsistent, I will say. Sometimes you just simply would not refer to the accumulator in an instruction like this as well. But some of them you do, some of them you don't. I really scratch my head on that, why the Z80 was inconsistent. At least the 8080 is very consistent. You would say add B, add D, add H. You would say ORA. That's all part of the mnemonic. And then you say space D. So all these are mnemonic space one register number, okay? So the register numbers all given here go into these 3 bits, okay? Now, this is an interesting feature of the 8080, the 8085, and the Z80. All have this pretty straightforward. Yeah, the accumulator A, B, C, D, E, H, L, all these registers are pretty straightforward. They're all 8-bit registers. They work like registers. They're 8-bit registers stored in the CPU and everything else. Then you got this mythical thing. There's kind of a virtual register called M. Now, this is the 8080 way of representing this. The Z80 represents whenever you see an M in an 8080 assembly language program. In the Z80, you would say something like this. Here's part of a Z80 instruction reference. And you would put HL in parentheses like this. So if I said load, C, comma, open parenthesis, HL, close parenthesis, what I'm doing there is the same thing on an 8080. That would actually be a move instruction, by the way, not one of these ALU type operations. But my point is, when you say M, when you're referring to a register on the 8080, the Z80 will exact same thing. We'll just put it in HL in parentheses like that. Those are literally the same thing. And in fact, if you look at this particular table of various values here, you see them grouped into 3s. Here again is like, which register do I want to put into, do I want to use as the destination? I want to read something out of memory and I will put it into register R. It's 3 bits. Notice this value here is 110, by the way. It's no coincidence that 110 shows up there to represent this virtual register M here, okay? So it is this encoding of these instructions and several other ones. If you scroll through here and just pick them at random, several instructions are grouped into these 3s and 3s and 3s and 3s just because of the way the chip is designed. Now, that's not always true. Here's a 3 and a 2 and so on. But the point is, if you do a lot of coding and you're going to use the front panel switches, you get really used to remembering that the accumulator, to this day, I know that's all 111. It's octal 7. Okay, the HL or the M register was 6, so that'd be 110. If we go back and check again, pretty sure I'm right about those. And B is like register number 1. Oops, I was wrong. B is 0 and so on. But M is 6, right? A is F, or rather 7, all ones. Here I am still forcibly thinking in hex, even though we're talking about octal here. So, okay, so my point is, why did they choose to do this and drive me nuts personally? Well, it's because I learned on the Z80 with a screen. I didn't learn first on day one with these switches, and I didn't have to work in binary. I could work with mnemonics in my source code, in my, at that level on my day one. But I will say that to this day, I still know several opcodes off the top of my head. 3E is, basically load the accumulator with an immediate operand. And that's in hex, of course. And all ones as an instruction is restart 38. And we'll talk about that in a minute when we get to this protect button over here. I'm painfully aware that all ones FF in hex or 377 in octal is a restart 38 instruction. Okay. Anyway, you get used to remembering them, and because of the way they're encoded on the 8080, are in groups of 3, 3, and 2 anyway, this turns out to be pretty natural. If your experience is from this manual here, and this is probably all there really was on day one for most people, Here's another instruction. What is this one talking about? No op instructions, data transfer. Yeah, this is your move. So what do we got here? That would be, yeah, if you want to move the value from register H to register B, I would put a 0 in the destination. I would put a, whatever that is, a 4 in the source, and I'd set these to 0 and 1, and that would just copy the value from H into B. All right? So when you're working with a manual like this, and looking at a panel like that, it is kind of natural to do this, provided that you just ignore all of what's going on over here. Okay? So while it seems weird to me, and it might seem weird to a lot of people that weren't around in 1975, myself included, there is a reason for this. Okay? Now, I never used the Altair. I have used 8080s and 81, 82, and that was in those years. I did spend a lot of time with these things. So, you know, your first real experience with a machine like this is going to influence your perspective a lot, I'm sure. So my warped brain operated in hex from the onset. So this, to me, is the natural way to go. If you started by reading the 8080 instruction manual, this may be the way to go. All right, so much for the groupings of these switches. That's got to be what's going on there. Now, the protect unprotect switch here and this light over there. Now, as I said, I'm painfully aware of restart 38. Let's go find, there's got to be a table down here in the manual where it says, here's all the opcodes of all the instructions. Boy, this is not easily done. Maybe this has got some OCR. If I do RST, there we go. There you are. 1 1 AAA 1 1 1. So this is all binary ones. The triple A there. If we look up the actual instruction, unfortunately, it's not easy to find. Here we go. The RST. There you go. Somebody hacked up this manual and put some notes in there. Okay, so wow, that's a 7, but looks a little bit like a 1. What's your handwriting if you're going to mark up a manual like that? Okay, so what do we got? If you said RST and you put 3 1s in here for this EXP value, which can be 000 to 111, what happens is it says it loads the program counter with this address in binary. It's all zeros, and these 3 EXP bits that come from here are placed here in the program counter value. So you end up with values that are all multiples of 8 because they end with 3 zeros over here, okay? And the biggest one that you can put in here would be if this was all 1s, and that would be in hex a 3 8. Okay? So one of the instructions is RST 38. So anytime we run into all binary 1s, it's going to execute restart 38. Okay? Now, what does that really mean? Now I'm speaking in hex, of course. It's going to go to address number 38. What does the restart instruction then do? Well, it is a 1-byte call instruction. And the idea is that there ought to be more of a detailed description in here somewhere. It gets caught up in using it for interrupt handling, which is really a huge value that this instruction has. But we don't even need to talk about that, because anytime you want, you can execute a restart instruction. And what it does, now they refer to it as a subroutine jump. I would have referred to it as a call, because that's literally what it is. What it does is it, here you go, it will push the program counter value onto the stack, and this is critical. Then it loads the program counter with this value down here that I already described. Okay, so every time you execute a restart instruction, it's simply calling a subroutine. There's really no more to it at all than that. The reason that this is different than the call instruction has to do with the way this chip was designed to handle its interrupts. And when you handle an interrupt on an 8080, what happens is the interrupting device can give it one single byte, a 1-byte instruction that the 8080 will execute. And the idea is, if you have these 1-byte subroutine calls and you have 8 of them, Then you have vectored interrupts. So if a device says, here, I'm going to interrupt the CPU, and the CPU comes along and says, okay, I'm acknowledging that interrupt. What do you want me to do? And he sends you down all binary ones. The CPU will just simply call a subroutine right then and there at address 0038 in hex. Okay, so that's when, if you're going to read about this, it gets all caught up in the, all this fun stuff about interrupt handlers. That's why interrupt handlers do nothing other than send a 1-byte opcode down to be executed. That's it. That's your definition of an interrupt on 8080. Well, this instruction is made to be paired with that for convenience purposes, to get you to allow an interrupt to be able to actually go somewhere and accomplish something, to vector out of what was happening. Now, the key to this is, okay, why all ones? Why am I talking about this? What does this have to do with protect? There's a lot to do with it. If you grew up in a day when you used machines like this, my first homemade system had a bunch of dip switches on it that I could toggle up and down, essentially the same kind of a thing as this, and far more crude and cheap. That was the key, I could toggle binary bits into the memory, and then I could make the CPU go. Basically all the same. It's just fundamental concepts, okay? Far more fragile, easy to break system. But all the same things. Very little money, and so I built mine with a Z80, and the amount of RAM, and this is the key here, was less than all 64K. And we've seen before, when you have a machine like the Altair or the IMSAI and you don't put 64K into it, what does the CPU see if it ever tries to read from memory that doesn't exist? It's just going to go out onto the database and say, give me what's there. Now, normally you have pull-up resistors on on databases that are driven in tri-states and stuff like that, and therefore the CPU would see all binary ones. Okay, now what would happen on a system like that if you ever accidentally branched into or simply ran off the end of RAM into an area, into an address, a range of addresses where there was no RAM at all? Well, the CPU would just get all binary ones, and it would execute that. That's a restart 38. What does it do when it gets a restart 38? It pushes the return address, as if you just made a subroutine call, into a stack, wherever the stack might be. Then it starts executing code at address 38. Okay? Now, what's at 38? Well, it depends on the design of your application. If you're wise, which I was not for a very long time, you might put something at address 38 that kind of goes into some sort of a spin loop or turns on an LED and stops to let you know that you just executed a restart 38, which means you probably branched off into the middle of nowhere and just stopped the machine from causing any more damage. Okay? Let's say you're not that bright. Let's say you're me in 1979 or 80 or whatever it was. And you let the machine go run rampant. Well, eventually it's going to execute garbage. And again, statistically, what are the odds that you end up running, branching off into nowhere again and reading from non-existent memory, getting another restart 38 and pushing more stuff into the stack? Well, if you only have like 1K, I think my very first machine actually had 256 bytes of RAM. Ouch. Well, if you only have, 256 out of 64K memory, right, or even 1K out of 64K of memory, just in simple percentages, if it is random, and I agree it's not, but the likelihood that you would read from non-existent RAM goes up when you have less and less memory in the system, which means that the odds are you'll eventually start executing some of these restart 38s. And the key here is that every time you do a restart 38, it will decrement the stack pointer and put stuff in the stack. And it's going to be doing this at a Ford versus Ferrari speed, okay? Nothing you're ever going to stop manually once this starts happening. So it was not uncommon at all for rampant programs on my systems to wander off into nowhere and constantly execute restart 38s at infinite speed, leaving me crying like Mr. Ford. Because the stack pointer would eventually wrap all the way around throughout all 64K, thus overriding every byte in the entire tiny amount of RAM that I did have in there, leaving me with absolutely no evidence of any kind as to what has happened to get me into that state. And leave me with the need to sit here. And if I had a machine like either one of these, I would have to retoggle in my entire program bit for bit and start all over again. Very frustrating. And crying in a whole different sort of way, and releasing no shortage of four-letter words when that sort of thing happened. Okay. I can assure you, you have all got stories if you're of a certain age. I'd like to hear about them in the notes below. What was your technique to prevent this from happening to you, right? Now, some of you will come over and say, I had an 8800 and therefore I didn't have to worry about it because I used the protect feature, which gets us back full circle to WTF is this LED and this switch that we don't have on the IMSAI 8080. I'll also point out at this point that the 8080, there's a hack in the manual for the 8080 that says if you want a protect switch, you can recycle this position here. You take the power switch off and you put a toggle switch on the back of the machine, and you can use this over here. You can put a circuit into the IMSAI motherboard to make it do the same sort of a thing that you get from the protect switch on the 8800. And the fact that that was a thing, as it were, means that there were people out there that had certain levels of frustration, like myself, early learners. I mean, you this is just something that happened to you all the time. It certainly happened to me. Okay, now, what does this do? How does it do it? And why does it do it? All right. Well, I hope you can realize that by now it has something to do with protecting memory from uncontrolled devastation of its contents. So this is a 1K static memory board for the MITS Altair. This thing was probably $250 in $1975. So what do we got over here? Let's have a look-see at parts of this schematic. What we got is a 15, 14, 13, 12, 11, 10. These come off the address bus. They're what do you got? The raw value and the inverted values are here, and these are little jumper wires. If you've ever seen a board like this, what you can do is you can put little jumpers in there. And the idea is, let's say you want this card to represent the first 1K of RAM at address 0. Well, what does that really mean? It means that for any address that comes out of the CPU or from the front panel that has all binary zeros in these bit positions, right? These are the most significant bit positions. If A15 0 and 14 0, 12 is 0, and I should have zoomed back in again. I'm sorry about that. 12, 11, and 10 are all zeros. We want this NAND gate over here to output a true, okay, which in this case would be 0. So you see CE bar, right? Chip enable bar, and then they invert it. Now it's true over here, okay? So what do? You go through a 15, you got and this is a 7404 inverter. So whenever A15 is 0, this is a 1. Okay, that's why they got these zeros and ones over here. So if A15 is 0, you connect up this to here. Okay, whenever A14 is 0, you connect that to there, and so on. Therefore, this gate will identify the situation when all these bits are 0. This will become true, which would put a 0 here and a 1 there. And if we follow this track up and around here, you'll see that this goes over to the right now. Let me see if I can get my arrow keys to work correctly. And it they marked it over here. It goes into this gate over here. Okay. Did I do that right? CE comes up and around over here. Okay, and then we go to the right. Oops. We go over here to the right. This is kind of hard to see, and then it goes up here and goes in here. You can see it's marked CE true right here. And come on, re-render the PDF, please. Thank you very much. Now, what's all this junk in here, right? Well, this is obviously a homemade D latch. When CE is true, one of these gates could go low, and which one goes low depends on prot and unprot. Aha! So these two wires run over to the left, down here, over to the left, and just go directly to the S100 pins marked prot and unprot. Okay? Now let's look and see what this thing does. Now, normally, the front panel will drive both of these low. We'll see that in a minute. So, the point being, if this board is ever accessed for a read or a write operation, whenever the address is such that it comes out and says, hey, I want to access this board. If these two are both low, neither of these gates can ever become true. Therefore, and they're NAND gates, so they're both going to be ones here. When you have a 1 and a 1 here, that is its latched state for this RS latch here. The combination of this whole thing being a D latch, that's the no change state, okay? Now, if prot was high, for example, when this thing was enabled, you'd have a 1, 1 in here, you'd have a 0 there. Whenever this is low, it doesn't matter what this is guaranteed to be high over here, and that would come down around like this. Now, by definition, if prot here is in fact high, we know, and we will know, that unprot will be low. And again, we'll see that on the front panel in a minute. Whenever that's low, that's guaranteed to be high, combined with a high over here, which guarantees that this will be low. Low comes back around here, which guarantees that that's not only high now, but stays high. And that's what causes this latch to latch onto. And remember that prot was the last thing that happened while it was enabled. The inverse is also true. If it's enabled and CE is high and unprot is high while prot is low, it'll flip around the other way. Okay, so these two pins here coming out of this this latch, this is the memory protect latch circuit is what's going to happen here, and this would PS bar over here. That's your protect status of this board. The idea is that if you set this flip-flop such that it is protected, these gates will prevent, if you come down and look where this gate here goes, okay, notice that the M write signal goes through this NAND gate. So if it wants to write into the RAM and this signal here is low, this, because it's a NAND gate, it'll always be high. It'll never be anything but high. And look what it's connected to and what it controls. It's the read and write signal. So if this signal here can never go low, I can never write into these RAMs. These are all 1K bit RAMs, okay? And every one of them has the ability to write gated by the output of this RS latch, this D flip-flop over here, okay? So what does it mean then to protect your memory? And how do you protect it? Right? Well, obviously, you can get the chip enabled to go high on the front panel if you ever examine a byte from the card, well, from any byte address that causes this card to become enabled. And if it is wired the way I described earlier, where all the most significant bits are all set to 0, that's when this thing will be enabled. CE will go high whenever the address bus is talking to the lowest bottom 1K. Now, if during that period of time, I decide to raise either prot or unprot high, I can cause this thing to flip. So the idea with the protect and unprotect switch, it allows me to control this flip-flop on this memory card. So if your memory card has this circuit on it, and you're using an Altair 8080 and you've just sweated for an hour and a half toggling in a ton of code, 1 byte at a time, you can go ahead and toggle in an address in the bottom K, just shut all the switches down, and then click protect. Hold this protect up, I suspect is what you'd have to do, while you examine. You then click the examine, okay? And it would cause that flip-flop to protect that memory. Then, if you ran a piece of code in there, and it went nuts, and it branched off into the middle of nowhere, and it executed restart 38 over and over and over and over again, and it pushed a bunch of stuff into the stack, it could never alter the contents of that 1K of memory on that card. I would have loved to have this feature back in the day. All right. Oh, my gosh. So anyway, that's what this thing is for. And later on, you want to be able to modify the memory in your program. You do the exact same thing, but you hold this in unprotect mode when you go ahead and do an examine on a byte whose address is in the range for that card. Of course, you need to have a pretty good set of awareness of what's really where, and the fact that what happens if I have 4K cards instead of 1K cards, right? Because then you'd be protecting it in 4K chunks instead of 1K chunks. Of course, those of us that had to save up money from paper routes and lawn mowings could probably only afford to buy memory 1K at a time. In my case, it was 2K at a time, because by the time I got into it, I was buying 2K RAM chips instead of these 1K jobbies that we had, 5-6 years earlier. So where then does the protect and unprotect signals come from? They come from the front panel. They come from right over here. This is a schematic of the Altair front panel, and you'll notice that it looks a lot like the 8080 front panel we've seen before. All these one-shot timers and stuff in here. Here's all the drivers with all the switches, with the pull-up resistors that are over on the CPU card, just like they are on the IMSAI system, so that you can then gate in your different switches, and you can also see that there's the person that marked this schematic up that note that the jump instruction and the no op instruction and the address high and low come from here, just like you saw on the IMSAI 8080. So very, very similar designs, okay, if not almost identical in many ways. Now, here is your protect and unprotect. Let's zoom a little bit more on that. What does it do? Well, if the run signal, okay, is low, and we come over here, the switch is normally not connected to anything. When the system is running, run would be high, okay? But when run is low, the system's not running, this essentially allows you to enable and disable this switch, is my point. So whenever we're not running, and this is a 0 here, what happens is you can shunt these pull-up resistors. So I can move it up to here and cause this signal to be a 0, which would cause this gate to output a 1 and go through a buffer and generate the protect signal. And you could flip it the other way while leaving prot high, which makes it low over here. This one then would go low, inverted, makes it high, and go over to the unprotect over there, right? So basically this switch will choose which one of prot or unprot will go high over here if the switch is moved up or down. So this is where you generate those signals, all right? So none of this is on the IMSAI 8080 front panel schematic unless you hack it and add it yourself. Okay? So that's what the protect and unprotect really do and how they work. Now I can see that I'm going into overtime here. So let's call this part 1. And next time we'll talk more about our kilobits game, and we'll see how this thing works and how this thing overcomes the shortcoming of the Altair that does not have these 8 LEDs up here. And we'll see that it's using these LEDs down here as its output display, which is kind of neat, considering it's really showing you the current value on the address bus. So tune in next time. We'll play some kilobits, and we'll look and see how that program works and how it can abuse the address bus to display values over here. All right? So thanks for watching. I'll see you next time.